All right, hello. Welcome back to our Math 2414 weekly reviews. So I hope you guys had a good spring break. So this week we're going to go ahead and cover section 9.4, models for population growth, 10.1, which is intro to parametric curves, and then 10.2, which is calculus with parametric curves. So let's go and get started with section 9.4. All right, so 9.4. Models for population growth. All right, so whenever we're talking about models for population growth, there are really two main models that we're going to go ahead and look at for this. Our first model is going to be our law of natural growth. Now, we did touch on this, I believe, in our last review. I believe this was covered in section 9.1. So essentially what the law of natural growth means is that our growth rate is proportional to our population. So essentially what this means is that as our population gets bigger, the rate at which our population is growing also gets bigger. If we have a small population, then that population will not be growing very fast either. And when we talked about this last week, we defined this as saying that essentially what this means is that our growth rate, dp dt, is equal to some constant k times our population. But what we're going to do this week is we're actually going to go ahead and expand on our law of natural growth a little bit more. So if we look at this, this can actually be treated as a separable differential equation. So let's actually go ahead and solve for that. What we need to first do is we need to go ahead and, of course, get our p's on one side and our t's on one side. So we can divide both sides by p to get us dp over p, and then move that t to the other side, so get us kt. And then we can go ahead and integrate both sides, k dt. There we go. And then we can go ahead and integrate both sides. When we get this, we're going to have dp over p, which will go to the natural log of the absolute value of our population, which is equal to kt plus c. We can go ahead and cancel out our natural logs by taking the exponential. So we get absolute value of p is equal to e to the kt plus c. And then what we can do is we can go ahead and we can break this up into say that we have e to the kt times e to the c. So now what we can do is we can go ahead and say that we so now what we can go ahead and do is we can let, since e of the c is some constant, we can let that be represented as a. And also, since we're working with population, we have to just kind of assume that it's going to be positive, since realistically we cannot have a negative population. We can also eliminate the absolute value. So we can now rewrite this as saying that P is equal to A times e to the kt. And then what we can also do is if we want to, so let's say they give us an initial value. So let's say they give us P of 0. If we plug that in, we get A times e to the k times 0. E to the 0 is 1, so therefore that's going to end up being just A. So therefore, our common characteristics of our natural growth model are going to be that, of course, dp over dt is equal to kp. And then, of course, our p of 0 is equal to a, which is equal to what we can call p naught or p initial. So therefore, what we can do is we can rewrite what we had as saying that if we integrate this, that our population is equal to our initial population times e to the kt. And another fun fact with this is that our relative growth rate which is essentially, our relative growth rate is essentially saying that our growth rate, what is our growth rate? So our growth rate is dp over dt divided by our actual population is equal to k from our first equation. So therefore, our relative growth rate is always constant. And then there's another scenario that we sometimes see. You probably won't get very many questions about this, but it's still a good thing to know. If we're talking about harvesting / immigration with an E, or like leaving at a constant rate, then that is going to equal, in this scenario, we're going to get dp over dt is equal to kp minus m, where m is our constant immigration rate. So essentially, that's like how much we are taking, our rate of like how much we're taking stuff out of the pool. So let's say that you every year we have a population of fish and a lake. Let's say every year 50 fish get pulled out of that lake. That would be our immigration rate. That 50 would be our 50 per year is going to be our constant immigration rate, or our constant harvesting rate. You probably won't get that many questions on this, but just in case it pops up, there you go. But this model, or law of natural growth, doesn't always take into account real life factors, because what this one is saying is that the population will just keep infinitely growing and growing and growing and growing at an exponential rate. But realistically, that is not possible, because essentially, as your population gets bigger, it needs resources in order to, you need resources in order to survive. So as your population gets bigger, your resources are going to dwindle, making it harder for your population to keep growing. And that brings us to the idea of the logistic model. And like I said, the main difference between our logistic the purpose for our logistic is similar, but just a little different from our law of natural growth. And the main difference is that in our logistic model, our growth rate is hindered as resources dwindle. And what this one is, and what this one says is that dp over dt is equal to kp times 1 minus p over m. And in this case, k is just a constant, p is our population, and m is our carrying capacity, which is going to be the maximum amount, like the biggest population that we can actually logically have. If you are below your carrying capacity, then you're still able to keep growing. If you're at your carrying capacity, you can no longer grow. Your population must stay at that rate, unless that population starts dying off or leaving, then it can start growing again. If your population exceeds your carrying capacity, your population will shrink in order to account for the loss of resources. Now, once again, this one can also be treated as a separable differential equations. It's kind of a long proof, so I'm actually going to go ahead and skip it. So just know that this is a separable equation. And if we integrate, and if we, play with it and integrate it, then we can say that P is going, then we can say that P of T is equal to M over 1 plus a constant A e to the negative kt. And also within that proof, when you play with our initial population, we can also say that A is equal to M minus our initial population over our initial population. So these are important formulas to remember. You will get a test, at least a couple, like at least one, if not like a few test questions over the logistic model. You may get like 1 or 2 over law of natural growth, but typically they're more likely to pull questions from logistic model, just because it's a little bit more complex. So let's go ahead and do an example with this. In this example, we are going to use the logistic model. And usually they'll go ahead and tell you which one they want you to use. If worst comes to worst, I would assume logistic. Just because, and you can usually also tell by context clues as well. So for this one, in this example, our initial population is 1,000. Our carrying capacity is 10,000. And if they give you, and even if they don't explicitly say it, if you get a carrying capacity, pretty good indicator you're going to be working with the logistic model. And then after 1 year, so P of 1, our population is 2,500. And what we want to know is what is our population after 4 years? All right, so first we need to go ahead and set up our equation to get in this format. So we can say that we have P of t is equal, we know what our m is. Our m is going to be 10,000 over 1 plus, we don't know our a just yet, but we can solve for it. So we know that if a is equal to m minus po over po, this is going to be 10,000 minus 1,000 over 1,000. We get 9,000 over 1,000, so therefore a is just 9. E, the thing is we still don't know our k just yet, so we're going to have to just leave that as a negative kt. But since we already have a defined point with that that 1 year population, we can actually go ahead and use that to solve for our k. So what we can do is we can go ahead and say that we know that after 1 year we've gotten up to 2,500 is equal to 10,000 over 1 plus 9e to the negative k times 1, so just negative k. All right, so if we go ahead and play with this algebraically, we can go ahead and get 2,500 times 1 plus 9e to the negative k equals 10,000. Then we can go ahead and divide both sides by 2,500. So therefore we can get 1 plus 9e to the negative k is equal to 4. Subtract 1, we get 9e to the negative k is equal to 3. And therefore e to the negative k is equal to 1/3. And we can take the natural log of both sides. So we get natural log of e to the negative k equals the natural log of 1/3. And therefore negative k is the natural log of 1/3. Which if you go ahead and solve for that, if you plug that in your calculator, you get negative k is equal to negative 1.099 approximately. So now that we know our k, what we can do is we can go ahead and plug that back in to our original equation. So then we can go ahead and say that p of t is equal to 10,000 over 1 plus 9e to the negative 1.099 t. Now we just have to go ahead and plug in our 4. P of 4 is equal to 1,000 times 1 plus 9e to the negative 1.099 times 4. And if you plug that into a calculator, you get about 9,000. So let's go ahead and try another example with the logistic model. This may be a different type of question they may give you. So for this one, they give us the equation dp over dt is equal to 0.4 p minus 0.001 p squared. And they also tell us that our initial population is 50. So what we want to know is, what is our carrying capacity? What is p prime of 0? And when will our population be equal to half the carrying capacity? So let's go ahead and get started with this one. So this one, it doesn't tell us exactly which model that we're using, but we can actually go ahead and use context clues to go ahead and use this to figure it out. Of course, they tell us carrying capacity in the problem, so you can assume it's going to be logistic. So if we think of our logistic model, we know that dP over dt is equal to Kp times 1 minus P over M. If we distribute this, we can say that we have Kp, that dP over dt is equal to Kp minus Kp squared over M. All right. So what we can do is we can see this is pretty much the same format that they give us our initial. So what we can do is we can take both of our terms and put them together. So we can say that 0.4 p is equal to Kp. P's cancel out, so therefore we know that K is just 0.4. We can also know that 0.001 p is equal, p squared is equal to Kp squared over M. Well, p squareds can cancel out, and we also know that we just solved that for K, so we know K is 0.4, so therefore 0.001 is equal to 0.4 over M, and then therefore M is equal to 0.4 over 0.001, which is 400. So therefore, we know our carrying capacity is 400. So now what they also want to know is, what is P prime of 0? So when we're looking at whenever we're looking at a growth model and they ask for P prime is just going to be our initial growth rate. So we have our initial growth rate. So we know P prime of 0. So we know. So what they're wanting to know is essentially what they're wanting to know is, what is our growth rate at our initial population? So they tell us that our initial population is 50. So all we have to do, let me go ahead and switch colors so we're not getting A, B, and C all mixed up. So what we have to do is just plug this initial population into our growth rate formula. So therefore, we just do dP over dt is equal to 0.4 p naught minus 0.001 p naught squared. So therefore, we get 0.4 times 50 minus 0.001 times 50 squared. And then this is going to come out to 17.5 once you plug that into a calculator. So now our last step I want to know is, when is our population going to hit half of our carrying capacity? So we know that our carrying capacity is 400. So what we want to know is what happens whenever we hit, So what we want to know is how long is it going to take for us to hit a population of 200? So from here, we're going to need to go ahead and set up our actual population formula. So we know our general population formula is m over 1 plus a e to the negative kt. Of course, where a is m minus p naught over p naught. All right. So we know that our m is going to be 400. We know that our k, since our k's are the same between our derivative and between our growth rate and our population, we know that k is still going to be 0.4. And then a, we can solve for a by saying that a is 400 minus 50 over 50. So we get 350 over 50, which is 7. So now we can go ahead and create a new formula for this, and create our formula for this one. So now we can say that P of t is equal to 400 over 1 plus 7e to the negative 0.4t. And since we know our population is 200, we can just go ahead and solve for t. So we get 200 is equal to 400 over 1 plus 7e to the negative 0.4t. 200 times 1 plus 7e to the negative 0.4t is equal to 400. Divide both sides by 2 and by 200, so we can get 1 plus 7e to the negative 0.4t is equal to 2. 7e to the negative 0.4t is equal to 1. E to the negative 0.4t is equal to 1 over 7. We can natural log both sides, so we can get natural log e to the negative 0.4t is equal to 1/7. Natural log of 1/7. Negative 0.4t is equal to the natural log of 1/7. Divide both sides by negative 0.4. T is the natural log of 1/7 over negative 0.4, which if you plug that into your calculator, you get T is equal to 4.865 years. So that one was pretty much just some review, some new stuff. Those are usually the types of questions you'll usually get for those. So now let's go ahead and move on to Chapter 10, which is parametric. So move on to Chapter 10. So Chapter 10 is covering parametric and polar curves. If you are planning on taking 2415 next semester, I would highly recommend paying attention and taking really, really good notes throughout Chapter 10 because this stuff will come back if you do take 2415. So let's go ahead and start off with start off with section 10.1, which is parametric curves. All right. So first, let's talk about what are parametric equations. So parametric equations are essentially equations to where, so okay, let me go and do some preface. So normally whenever we work with regular equations, we normally just work with x and y. So usually x and y are functionally related. So y can be a function of x can be a function of y. But parametric equations are a little bit different. So parametric equations are essentially when x and y are defined by a third variable. So essentially what this looks like is, what this means is that x is equal to some function of t, and y is equal to some function of some other t. So we can see how x and y they're both on the same graph, but they're both defined by a different variable, in this case t. And that third variable is what is referred to as a parameter. That's where we get the term parametric equations. So yeah, both of these are related, but there's separate equations that are both related by having that same variable. So whenever we move on a little bit further, it may make a little bit more sense. So parametric curves are essentially curves generated by parametric equations. So let's go ahead and go over how to actually sketch these parametric curves, because this may make some of the conceptual stuff make a little more sense, since this is a pretty visual concept. So let's go ahead and talk over about how to actually sketch this. So our first step that I would do is build a table and you want your columns to be t, x of t, and y of t. Step 2, plot points based on table. And usually, and you want these to be in order of t. So if you have if your t values are 1, 2, 3, 4, you want to plot those in that specific order. Because if you go 2, 3, 4, 1, yes, you get the same points, but what we have to do is you actually have to go ahead and connect them. So that's why you want those in order. And the other reason why you want them in order is that typically if you're doing this on paper, they usually want you to draw arrows indicating the direction. So whenever I'm dealing with sketching parametric curves, T can be bounded. So they may give you a list and say that A is less than or equal to T, which is less than or equal to B, or unbounded. So essentially where your range is from negative infinity to infinity. Now, if T is bounded, you typically you will have what is called an initial point, which is essentially going to be when you have your minimum T. So that's essentially going to be equal to your XY point is going to be X of A, Y of A. And then your terminal point is going to be X of B, Y of B. So let's go ahead and just do an example of how we can actually go ahead and graph and visualize parametric curves. So in this example, we have the curves. We have x is equal to t cubed plus t, and y is equal to t squared plus 2. And we're also going to bound our curve from -2 to 2. So our first step, of course, would be to go ahead and draw out our table. And we said we want t, x of t, and y of t. So in this one, let's just go ahead and just do all of our integers within our bounds. So -2, -1, 0, 1, and 2. All right, so if we plug -2 into our x equation, we're going to get -2 cubed, so -8, plus a -2. So we're going to get -10. If we plug -1 into x, we're going to get -1 cubed minus 1, so -2. Plug in 0, we get 0 plus 0. 1, we get 1 cubed plus 1, so 2. And then if we plug in 2, we get 2 cubed, which is 8, plus another 2, so 10. Now if we move on to y, we get -2 cubed, so 4 plus 2 is 6. -1 squared is 1, plus 2 is 3. 0 plus 2 is 2. 1 squared plus 2 is 3, and then 2 squared plus 2 is 6. So now it's time to actually go ahead and plot our points. All right, these are all in the first and second quadrants, so I'm just going to kind of just draw that kind of low. All right, so then we're going to go ahead and have 1. And then we're going to go ahead and do this in 2s, just to save room. So yeah, 2, -2. And let's go and do the same thing up here. 1, 2, 4, and 6. So now we need to go ahead and plot our points in that order of t. So we start off at t. So we have our x is going to be -10 and our y is going to be 6. So we're going to start here. Then we move on to t is -1. So we get -2 and then go up 3. Then we go to t is 0, so we know x is 0, y is 2. No, I'm going to just do x's because this is going to not act right for me. All right, so now we're going to go t is 1, so we're back up to 2, 3. And then we go up to t is 2, so 10, 6. So now what we need to do is go ahead and connect our points in that right order. So we're going to kind of go down. We're going to pretend I hit that. Well, we'll pretend that looks a little cleaner, but that's the general idea. Oh, wait, that doesn't have an arrow. So we have our initial here and our terminal here. So what we do, our next step is just going to be to draw our arrows in the direction. So we're going to go from initial to terminal. So just kind of draw them along the line like this. And that is how you draw sketch a parametric curve. Now, you may have some instances to where you can go ahead and actually eliminate your parameter. So in some cases, you can actually go ahead and convert from parametric to Cartesian. So usually what you're going to do, if you want to do that, is solve for t in one equation, and then you're going to go ahead and plug that into the other. So let's say you're given your x of t. You can solve for t in terms of x, and then plug that t of x into your y to get you y equals f of x. This will make a bit more sense when we do an example. Sometimes you may also be able to use patterns. You may be able to look for patterns. Usually, usually with circles. And in that, because that's usually a pretty special case. So circles is the main one you would usually see this with. So for those, what you would get, so the pattern for that one would be, is if you have your x is equal to some h plus some radius cosine of t, and you have your y is equal to some k plus radius sine of t. And usually they're going to go ahead and limit your parameters to between 0 and 2 pi. And that's usually the main case where you'll see that. So let's go ahead and do an example with this. Do an example with both of these. So for this first example, what we want to go ahead and do is this one. We just want to go ahead and eliminate t, and they give us x is equal to t squared minus 3, and y is equal to t plus 2. All right, so if we look at these, what we want to do is solve for t in one of these. So the one that'd be easier to do is y, because that one t is linear, and we don't have to deal with having to solve for like positive and negative roots like we would for x. So what we can do right here is we can go ahead and say that y minus 2 is equal to t. So then what we can do is we can take this t and plug it back into x and say that we can get x is equal to t squared, which we said is y minus 2 minus 3. So we can say x is equal to y squared minus 4y plus 4 minus 3. So then we can finally say that x is, so we can just clean that up and say x is y squared minus 4y plus 1, and that is our final equation, and we have eliminated our t. So I have one more. This one's going to be a mix of sketching and we're going to go ahead and both sketch and eliminate the parameter. So yeah, we're going to sketch with our parametric. Then we want to go ahead and eliminate t. And our equations for this one are going to be x equals sine of t, y equals 1 minus cosine of t, and then t is going to be bounded between 0 and 2 pi. So our first step is going to be to go ahead and build our table. So for this one, let's go ahead and do every one of pi over 4. So we're going to do 0, pi over 4, pi over 2, 3 pi over 4, pi, 5 pi over 4, 3 pi over 2, 7 pi over 4, and then 2 pi. And for this, what we're going to do is we're just going to go ahead and approximate square root of 2 over 2 to be 0.7. So, okay, we have x is sine of t, so sine of 0 is 0. Sine of pi over 4 is square root of 2 over 2, so 0.7. Pi over 2 is 1. 3 pi over 4, we're in the second quadrant, so it's still positive, so 0.7. And then pi is 0. 5 pi over 4, we go down to negative 0.7. 3 pi over 2 is negative 1. 7 pi over 4 is negative 0.7. And 2 pi, it goes back up to 0. Now, y we have 1 minus cosine of t, so we have cosine of 0 is 1, so 1 minus 0 is 0. Then we have pi over 4, so that's going to be 1 minus 0.7, so 1.3. Oh, I mean 0.3. Then we get cosine of 0. Cosine of pi over 2 is 0, so 1 minus 0 is 1. 3 pi over 4, we're in the second quadrant now, so cosine is going to be negative, so we get 1 minus, so yeah, now we get -1 minus a negative 0.7. So then we can get 1.7. Pi, we get -1, so that's 1 minus -1 is 2. 5 pi over 4, we're going to go to 1.7. 3 pi over 2 is going to go back down to 1. And then we go back down to 0.3, and then 0. So now let's go ahead and sketch our graph. So let's see, everything is in the first and second quadrant, so let's just not really bother. All right, so now we're going to go 1, 2, 1, 2, 1, 2. All right. So we start off at 0, 0. We move over to 0.7, 0.3. Move up to 1, 1. Move over to 1.7, 0.7. Move back up to 0, 2. Move over to negative 0.7, 1.7. Move down to negative 1, 1. Move over to negative 7.3. And we end up back down at 0. So if we go ahead and connect, I drew this a little wonky, but I drew the axes kind of wonky, but if we go and draw our arrows in, this is supposed to be a circle. It's supposed to be a circle that looks like this. I drew it wonky, so. So now let's go ahead and try to eliminate t. So for this one's a little different. So we can't necessarily just plug stuff in. But we can go ahead and use some patterns. So we see we have a sine and we see we have a cosine. So let's go ahead and try to square these. So we can say that x squared is equal to sine squared of t. And y squared is equal to 1 minus 2 cosine of t plus cosine squared of t. Well, if we put x squared plus y squared together, we get 1 minus 2 cosine of t plus cosine squared of t plus sine squared of t. This can go combined together to 1. So we can say x squared plus y squared is equal to 1 minus 2 cosine of t plus 1. So we only have that 1 t left. So what we can actually do with that is, since we know that's a cosine of t, we can go back and use our y to go ahead and solve for it. So if we know that y is equal to 1 minus cosine of t, we can go ahead and actually solve for cosine of t. So y plus cosine of t is 1. Y is equal to, cosine of t is 1 minus y. So therefore, we can get x squared plus y squared is equal to 1 minus 2 times 1 minus y plus 1. We get x squared plus y squared is equal to 1 minus 2 plus 2y plus 1. That 1 minus 2 plus 1 will cancel out to where we just get 2y. X squared plus y squared is 2y. And this is looking a little familiar, so we can actually go one step further, move that 2y over, and complete the square. So we get minus 2y, a plus 1 over here, and a plus 1 over here. X squared plus y minus 1 squared is equal to 1. So therefore, this actually matches our normal form from a circle that we learned way back at the beginning of the year. And if we look at our graph, we match it. It matches because this says that we have a circle with a radius of 1 with the center at 0, 1. If we go back up, that is exactly what we have. So now let's go ahead and move on to chapter 10.2. I may not be able to go ahead and do as many examples in this one as I would like, because this is a pretty dense section. It's not that hard, it's just dense. So section 10.2 is going to be calculus with parametric curves. So, of course, our parametric forms are going to usually be x is some function of t and y is some other function of t. So first, let's go over and talk about derivatives. So with derivatives, if we play with our chain rule a little bit, we can actually end up getting the formula dy over dx is equal to dy dt over dx dt, as long as dx dt does not equal 0. So yeah, this is essentially based on our chain rule, if you go look that up in the book. But essentially what this is saying is that our derivative of our parametric curve will be the derivative of our y function divided by the derivative of our x function. So now there's a couple things, of course, we can still do with our parametrics, with our derivatives. We can still use our tangent. We can still use this to solve for tangent lines. All right. So like we learned way back in at the beginning of 2413, when we're dealing with the tangent line, our slope is going to just be our dy dx, and that carries over here. And also, just if this comes up, if dx over dt is equal to 0, that means you have a vertical tangent line. And that makes sense because essentially if your dy dt equals anything other than 0, that implies that it's moving in some direction, up or down. But if your dx dt doesn't change, then that implies that you're not moving side to side. So therefore, that makes sense that your points would just be going straight up or straight down, which would get you a vertical tangent line. So let's go ahead and do an equation with this one. Let me do an example, I mean. So find the equation of the tangent line whenever we have the curves x equals square root of t, y equals t squared minus 2t, yeah, and y equals t squared minus 2t. And we want to do this whenever t is equal to 4. All right, so like we said earlier, m is equal to dy over dx, which is dy dt over dx dt. So essentially, our first step we're going to do is we're going to take the derivative of y. So derivative of y is going to be derivative of t squared is going to be, yeah, dy dt. We're going to derive that. T squared goes down to 2t, and then 2t goes down to negative 2. Our dx dt, so we have x is t to the 1/2, which will go down to 1/2 over square root of t. So therefore, our dx dt, so therefore our dy over dx is going to be 2t minus 2 over 1 over 2 square root of t, which we could actually even go ahead and move back up to the numerator. So we could say we have 2 square root of t times 2t minus 2. So now we just have to plug in our value for t. So we get 2 times square root of 4 times 2 times 4 minus 2. 2 times 2 times 8 minus 2. 4 times 6. So therefore our slope is going to be 24. So now we just need to be able to find a point. So we can use t to find our xy point that we can use to find our tangent line. So x of 4 is going to be square root of 4, which is 2. Y of 4 is going to be 4 squared minus 2 times 4, so 16 minus 8, so 8. So now we can just plug it in and say that we have 8 is equal to 24 times 2 plus b. A is equal to 48 plus b. B is equal to negative 40, so therefore our tangent line will be y is equal to 24x minus 40. Another thing that we can do with our parametric derivatives, of course, is concavity. So we have solved our first derivative, but now we need to go ahead and take the derivative again. So our formula for our second derivative is going to be our second derivative, so d squared y over dx squared is going to be d over dt of dy over dx. So the derivative of your first derivative divided by your dx dt. All right, so now let's go ahead and do our yeah, we have time for an example for this one. This one is going to be when is the curve concave up. And in this case, we're given x is equal to t cubed plus 1, and y is equal to t squared minus t. All right, so our first step we need to do is find our dy over dx. So therefore, we can say that, let's first find our dy dt. So our dy dt, so we go t squared goes down to 2t, t goes down to -1. Our dx dt, we're at t cubed goes down to 3t squared, and then plus 1 goes down to nothing. So therefore, our dy dx is going to be 2t minus 1 over 3t squared. So now we need to go and find our second derivative, which of course is the derivative of our first derivative over our dx. So first of all, let's go ahead and find the derivative of our dy dx. So this time we have our quotient rule. So we're going to do our low so 3t squared times the derivative of our high minus our top minus the derivative of our bottom all over our bottom one squared. All right. So let's go ahead and clean this up a bit more. Clean this up a little bit more. So we're going to get 6t squared minus, we get 2t times 6t, so minus 12t squared minus a 6t. Go and distribute the negative. We get 6t minus 6t squared all over 9t to the 4th. And then we have to divide all of that by 3t squared again. So therefore we get 6t minus 6t squared all over 27t to the 6th. We can go ahead and eliminate a little bit. So let's go ahead and get rid of a 3 and get rid of a t. So if we get rid of 3, we can get 2t minus 2t squared over 9t to the 6th, and then go one step further and get 2 minus 2t over 9t to the 6th. All right, so like we did back in Cal 1, we still do our second derivative test. So let's go ahead and see. We know it's going to be undefined at 0, and then it's going to be equal 0 at 2 minus 2t equals 0, so at 1. So we can go ahead and set up our bounds. We can get negative infinity to 0, 0 to 1, 1 to infinity. All right, so if we plug in -1, we get 2 minus 2 times -1 over 9 to the -1 to the fifth. So therefore, we're going to get 2 plus 2 over -9, so that's going to be a negative. If we plug in 1/2, we get 2 minus 2 times 1/2 over 9 times 1/2 to the fifth. That's going to be a 2 minus 1, so a positive over a positive, so therefore a positive. And then if we plug in 2, we get, if we plug in 2, we get 2 minus 2 times 2 over 9 times 2 to the fifth. And then therefore we get a negative over a positive, so therefore a negative. Therefore we are concave up from 0 to 1. All right. So, all right, so now let's move on to area under a curve. So area, I don't think you typically get that many problems. I don't remember getting a ton of problems on area when I took this course. That could be a little bit different. All right, so for area, the main thing you need to know is that, let's say that we know that we have y is equal to g of t, x is equal to f of t. And then we also know that alpha is less than or equal to t, which is less than or equal to beta. And then g of t is greater than 0. Then your area under that curve would just be your area is equal from alpha to beta of g of t times f prime of t dt. And that's pretty much based off of the idea that whenever we work in Cartesian, we go from a to b of your function y dx. So I'm not really going to do an example on that one because I don't remember, like I said, I don't remember getting a ton of questions on this. And so let's go ahead and move on to arc length. Yeah, this section, like I said, it's not super, super hard, but it's dense. So arc length. Once again, it's kind of the same idea as with area. You have to meet pretty much the same stipulations. In that we have x is equal to f of t, y is equal to g of t, t is in between alpha and beta, and then we need our f prime and our g prime to be continuous on our interval from a to b, or alpha to beta, close bracket. So the formula for this is going to be your arc length is equal from alpha to beta of the square root of dx over dt squared plus dy over dt squared dt. So let me see. To save time, we're just going to do just setup for this one instead of solving the full thing. So for an example for this one, we are given the curves x is equal to t sine of t, y is equal to t cosine of t, and then t is in between 0 and 1. All right, so let's go ahead and start on this setup. So we know our alpha and beta are going to be 0 and 1 times the square root, and we're going to have our dx and our dy. So let's go ahead over to the side and solve for those. Dx over dt. So we're going to have to go ahead and use our product rule right here. So we're going to do t times the derivative of sine, which is cosine, plus t times, oh wait, t times the derivative of sine, which is cosine, plus sine of t times the derivative of t. dy dt, we do the same thing. We get t times the derivative of cosine, which is negative t sine of t, plus cosine times the derivative of t, which is cosine. All right, so now what we can do is we can go ahead and plug, go ahead and plug these in and square them. So we're going to get dx dt, so t cosine of t plus sine of t squared, plus we're going to do cosine of t minus t sine of t, just to make that look a little prettier, squared dt. Let's go ahead and simplify this a little bit to get us t squared cosine squared of t plus 2t cosine of t sine of t plus sine squared of t plus cosine squared of t minus 2t cosine sine plus sine squared. All right, let's see if there's anything in this massive thing that we can eliminate. So we have a 2t cosine sine and a minus 2t cosine sine, so those can be eliminated. And then we also have a sine plus cosine, which can go down to 1. So we can get down to square root of 1 plus t squared cosine squared of t plus, oh yeah, that's a t squared right here, plus a t squared sine squared of t. We can go ahead and group these up to simplify down to t squared we can break that down like this to where we are left with 1 plus t squared dt as our integral, and at that point you can just solve for the integral. So then I have one last little subtopic left to touch on, which is going to be surface area of a revolution. So the stipulations for this are once again pretty similar. X is f of t, y is g of t, alpha and beta are the bounds, f prime and g prime are continuous, g of t has to be bigger than 0. And usually when we're doing this, we're going to rotate about the x-axis. And if this is the case, our formula is going to be from alpha to beta of 2 pi y times the square root of dx over dt squared plus dy over dt squared dt. So that is about all we have time for today. I'm sorry I didn't really have time to get into more examples in section 10.2, but hopefully this is helpful today. Good luck on your quizzes and such. Have a great day.